I decided to present for you a special subject. Lines of antigen-antibody reactions in vitro. Investigate basically the significance for the development of sensitive and specific antigen and antibody assays. To some extent, their possible significance for my name is Viggo Bitsch, a biomedical researcher and administrator. I've been working in various fields, but especially in the antigen antibody elaboration of antibodies and antigens. Define my activity. I have never been presented to a mathematical problem I couldn't solve. To me, you could say, if you say that we think on that field are quite philosophical, the researcher would say, yes, that starts facing you. What about the outside? Or early, let's have a problem. Here. Okay. But when I played chess with him, I soon learned to beat him. I felt that he too early jumped to the conclusion about the next best move. So as a child, I decided to become a researcher using, well, my talent for complicated or, let's say, systematic analysis of problems. Later, when I had to decide on the university study, I decided to go for veterinary medicine. There were two reasons, but one was you can't make experiments with humans. That's impossible. You can make experiments with animals. But what I did not foresee was that veterinary researchers, bioresearchers in the human biomedical world did not consider veterinary researchers of interest. They were a sort of second-class researchers in their minds. That's what I felt. why did I become interested in antigen-antibody reactions? Because we had an outbreak in an artificial insemination bull center where the infections were spread with semen from that bull to numerous cows inseminated. That was not acceptable. We will just jump to this figure. We immediately started an experiment of the genital infection and also nasal infection in a bull. Another bull was kept as a contact bull. And what you see here is in line 2, risk shedding of bovine herpes virus infection. The figures indicate weeks, not days. This bull was followed over a period of more than 2 years. And you will see many periods of risk shedding of virus from that bull, supporting the conclusion that you cannot accept infected herpes virus infected bulls at insemination centers. You cannot allow the infection to be spread from the bulls. So that led to the Danish pioneering conclusion that we had to eradicate herpes virus infections in bull centers. We didn't wait 2 years. We had very early results indicating that the infection would be reshed later on. And then you will say that, well, the virus survives in the central nervous system or the ganglia. Well, it's the possibility, but there's another possibility that is even more likely. Virus may survive in germinative cells in the mucous membranes or cutaneous membranes. Okay. We had a contact bull. Bull was infected nasally because this bull was infected at the same time by the prepuce and also by the nose. We had to control the infection. We had to be sure that our tests were good enough, safe. So I had to perform preliminary investigations to find out, could we do better? Could we be more safe? And I immediately found that we could test serum undiluted. Not diluted 1 in 5 and 1 in 10, as many people did, but we didn't want to throw away a sensitivity factor of 5 or 10. That's one thing. I also found that the sensitivity was dependent on the virus dose and highly dependent on the reaction time. So we ended up soon with a routine test for animals to be introduced to artificial insemination centers with a reaction time at 37 degrees, 24 hours. And then, of course, I wanted to know why we achieved that result, that conclusion. To illustrate the importance of that highly sensitive test, you will see results here from examination of blood samples from 2 herds. To the left, the conventional the conventional test, also today, the one accepted by the WHO to be the gold standard test for demonstration of antibodies. By the way, why is WHO called World Health Organization? Why it's not called World Human Health Organization? There's also a World Animal Health Organization. Illustrates what I just mentioned before. To the right, you have an almost normal distribution with the extremely sensitive test of the antibody titers recorded, and there were 19 animals that were found negative by the gold standard test that became positive in the highly sensitive testing, and the animals that were antibody negative were the animals that were young, all. Only one young animal, aged 1 year, had a clearly positive reaction, indicating that for 2 to 3 years had been comprehensive spreading of the infection in those 2 herds. So I decided to investigate, find out about the neutralization lines. If we delve into the world of biology, we will, to a wide extent, see a new world. We'll see a world where 2 cells, 1 cell divides, become 2 cells, 2 cells divide and become 4 cells, and we record antigen titers, we record antibody titers by logarithmic values. So the new biological world is, to a wide extent, a logarithmic world. And I realized that I would have to, also when I recorded reaction time, I would have to record reaction time logarithmically. That means, it doesn't function, that if we record logarithmically, we have here the base 2 logarithms, and that means that here this log unit represents 2.5 minutes, here 5 minutes, and here 40 minutes. If I had recorded those reactions I've achieved here with 3 different antibody samples, a high level, a medium level, and a low level, in the usual arithmetic way, we would have had lines flattening out. But now, in the logarithmic world, you will see, oh, that's interesting. What's the continuation of these lines? Wow. Do you see what I see? Still, logarithmically, with extended reaction times, we see, in fact, a reaction that is approaching a straight line with a slope of 1. Look at this first order equation. That's the normal way to describe a first order reaction. The y-intercept b is not important here, but if you transfer this first order reaction into a log reaction, a log equation, you will see that the slope A, the value indicating the slope of the straight line, that way, or even negative, disappears. You will have, in the log world, you will have a slope of 1, 45 degrees centigrade. That's what we see here. The reaction is approaching first order reaction. And then you'll be curious again, what's the continuation? With excessive reaction times, this time with various reaction temperatures shown also, you'll see a first order reaction. Here we included various virus titers, or let's call it in a neutralization test, various doses from 25 units to 250,000 units. And you see a wonderful result. Now I could present the formula for the reaction between antigen and antibody, not influenced by what we'll learn later are aggregation reactions. The pure reaction between virus and antibody. Now the formula is smaller. I just wanted to show to you how important this formula is. From this formula, you can decide the sensitivity that you want from your test. Sorry. Antibody and antigen are antigen and antibody and antigen titers. T is the reaction time, and K is a sort of velocity. The velocity, the rate of antigen and antibody reaction. You'll see the fraction to the right is an expression similar to kilometers per hour. So it's a velocity. But I call it the standard reaction rate factor, because if you have mixed antibody, the standard reaction rate factor is already determined by the system. Now you'll see a new term here. You'll see the factor Q. What's the factor Q? The factor Q is also a determiner of the reaction rate, but it may be difficult to understand. Where is the temperature? It's not shown, and I found out I didn't need to show the temperature because the factor Q is temperature dependent. The factor Q was a new determiner that I didn't foresee that we would find. But what's the factor Q? It's simple. Here, if it goes from here horizontally to the next line, you will see what is required in time. You will see what is required in time to neutralize 10 more virus units. Or if you move from here, you will see what's required by antibodies to neutralize 10 more units. That distance symbolizes the factor Q. I think you should notice one thing. The titer recorded after 24 hours at 37 degrees centigrade will not be achieved at room temperature until after 4 days of reaction. If you go down to a reaction temperature of 4 degrees centigrade, you will not achieve that same sensitivity until after reaction for 16 days. That illustrates that you shall never perform a test at a temperature lower than 37 degrees centigrade. What's the factor Q? I illustrated the factor Q, actually. I characterized the factor Q as the log antibody, log virus equivalence factor of neutralization. And that's correct. We are in the logarithmic world here. I must underline what I investigated was the reaction between herpes virus and IgG antibodies. Now one thing more. I found the first order reaction valid for antigen-antibody interactions. But why did we have this fast reaction here with very short reaction times? I did not have at that time, 40 years ago, I did not have the explanation. But a couple of years later, a Belgian groom reported that viruses that were aggregated by antibodies were neutralized. And then I had the obvious explanation for what I call the over-neutralization reaction, the reaction more pronounced than the regular reaction represented by my formula. So what we have here, after 2.5 minutes, we reach a reaction that is in fact explosive. Anybody recording in arithmetic ways would see that this reaction is flattening out, decelerating. They will conclude that this reaction has reached its peak relatively soon. But that's not the case. if we look at the problem logarithmically. But there's another aggregation reaction. The effect of the complement component C1q. C1q has the ability to attach to antibodies, the Fc region of antibodies, but only to antibodies that have been bound to its antigen. Then this antibody will become sensitized so that the C1q will attach immediately if C1q is present in a sufficient concentration. So I wanted to investigate that, also performed neutralization reactions with and without C1q on early antibodies, meaning that these antibodies comprise also IgM antibodies. And you see to the right, controls here without C1q. Here, if C1q was added immediately at the start of reaction. Here, up here, if the line 2, 1 hour before the first recording here, the line 3, 1 hour before the first recording here, and the reaction 4, where C1q was added after 23 hours. And you see again, in this logarithmic system, you'll see a first order reaction with IgM antibodies. The IgM antibodies were in surplus, of course, so we record IgM antibodies. C1q will react with all antibody classes. That was the initial investigation. But remember, a first order reaction does not include that reactions between antibody and antigens can result in an equilibrium state. That's impossible. And that's the opinion by most people in the human biomedical community, also in the immunological community. So let's go to the next. What is shown here is the appearance of the not neutralizing and neutralizing IgM and IgG antibodies following nasal infection with the herpes virus. Up here, you have titers by not neutralizing IgM antibodies. Here, the next line, neutralizing IgM antibodies. Here, not neutralizing IgG antibodies, and here, neutralizing IgD antibodies. What are neutralizing antibodies? Neutralizing antibodies are the antibodies that by attachment to a virus will neutralize that virus particle immediately. Not neutralizing antibodies will not do that. A virus can be covered, attached to as much as 50 different not neutralizing antibodies, and it will still be infective. That's the difference between neutralizing and not neutralizing antibodies. And that figure here, I think, will be almost impressive for you, isn't it? You will never see such results from investigations in humans. Okay. Antibodies and antigens are attracted by a specific force. That force has been measured by microbiologists, but these microbiologists did not foresee, did not realize that also the existence of that force also involved that these binding sites would be attracted to each other by a magnetism-like force. They didn't realize that such force would require to be magnetism-like. They are attracted. Antibody sites and binding sites, antigen binding sites, will never be able to find each other if they are not attracted by a magnetism-like force. And then we have the C1q component of complement. This element has exactly the same situation. It will bind to the Fc region of an antibody, sensitized by being bound to its antigen by a force that also functioned in two ways. It's biphasic, initially a magnetism attractive force, and then an exact binding force. Now, I shall tell you a tale. Millions of years ago, nature realized, after having constructed this simple antibody molecule, not with two arms, only the one arm, she realized that she could improve the fight against infectious agents enormously by introducing a new element in the fight, namely aggregation. Therefore, she, in step 2, after the insertion in step 1 of a second arm, both with their binding sites at the tips of those two arms, enabling the antibody to attach to different antigens, aggregating. The next step was, polymerized antibodies. Here, the secretory IgA antibody, and here the pentameric particularly IgM antibody. Here, the C1q structure that is hexavalent. They're not stiff. They are flexible. One arm is capable of snatching here, catching, and immediately, if they come into range of the magnetism force, they will clash together immediately. That's an explanation of the explosive binding between antibodies and antigens, as I have explained to you as the principle of aggregation. Okay. Now you can tell me, was my tale, was it almost true? Was it fantastic, a fairy tale, or was it just airy? We have three ways of aggregating or inactivating viruses. Two aggregation methods and the method by the neutralizing antibodies. There are so many false hypotheses in virus-antibody interactions. The equilibrium theory of neutralization or binding, the occupancy theory of neutralization. But so I understand. So sometimes I feel that my life's task has been to bring order to chaos. The law of research, not so relevant at this time, not so relevant. I tried to publish, not always with success. People didn't understand what I had to introduce, but nevertheless, gold standard assays are two, one for neutralizing antibodies and one for non-neutralizing antibodies, all with standard reactions. One last demonstration. If I ask you, if you double the reaction time from, for example, 3 to 6 hours, how much more virus will be neutralized by the same amount of antibody? 100 times more virus. Oh, that's incredible, isn't it? If you increase the reaction time by a factor of not 2, but a factor of 4, how much more viruses will be neutralized? 10,000. It's incredible, isn't it? You can increase the sensitivity of a test for demonstration of virus by enormously by increasing the reaction time. Now I will just say, you can go to my home page. There you will see important, what I feel are important publications. You will see also comments that I have included for each publication. So that will finish my presentation today. Thank you.